D'Alessandro from Southampton University to deliver his talk entitled Using Zero Manifolds to Model Little Crystals in Q-tensor Theories.
Thank you for the organizer for having me here. Thank you to you for risking being late for lunch to be here. This talk is a work that has been done in collaboration with my ex-PhD student Keith Daly and with the help and support of other people, some of whom are in the audience. David Chillingworth was helped when the mathematics was too hard, and Tim and Malgosia Kaczmarek that helped when the liquid crystals were too hard. It's also a talk in the same line as if you want how to use mathematics to make numerical codes more efficient. At last week's British Applied Mathematics Colloquium, there was a talk by Doug Arnold from the University of Minnesota, I think, saying he's a numerical analyst. And so he made this statement that caught me by surprise, that in the 1950s there were 6 grid points between Los Angeles and New York in weather forecasting programs. Now there are far more. And the increasing in the power of predictions is not just due to the increase of computing power. He said that the computing power has increased by a factor of 10 to the 7. The major increase is in the power of the algorithms. The efficiency of algorithms has increased by a factor of 10 to the 12. So this does not hope to give 10 to the 12, but maybe 10 to the 1, or something like that. So what do I want to do in this talk is to explain a little bit the origin of this project, and then realize that there are slow manifolds in liquid crystals, and then attempt to use them to speed up numerical simulations of liquid crystals under some approximations. And I will mainly focus on the assuming I can use the there is an on-off switch. That I have pushed off. There it is. I will mainly focus on 2D and leave 3D for the very keen and interested readers. So what do we do with liquid crystals? Well, we just consider, at least for the moment, nematic liquid crystals that are in a they are in a ordered phase. They are described by a Q-tensor, and the Q-tensor is a traceless symmetric tensor, and so it's described by 2 parameters in 2 dimensions and by 5 parameters in 3 dimensions. And the way you use to parameterize this Q-tensor is an idea that we picked up from a paper by Andres Sonnet. That's to represent the tensor on a basis of traceless symmetric tensors. So we never write Q, we always write these vectors A. If you are in 3 dimensions, there are 5 linearly independent tensors, and there are these 5 here, and they are orthonormal with respect to an inner product, which is the trace of the product of 2. If you are in 2 dimensions, there are only 2, and so this makes it quite convenient because you can represent easily the geometry of the liquid crystal in 2 dimensions just using these 2 parameters. And then the liquid crystal is described by a free energy. And again, the details of the free energy are not particularly important. In this case, we have chosen the simplest of free energies. That is, it's a one elastic constant approximation. There is an exists term in nabla squared A. There is a coupling with the electric field, which is this. And then, if you want, the Kindle-Landau part of the free energy. And then these can be more complicated if you want, but at the end of the story, it doesn't matter from the point of view of this presentation. The key observation is that the terms in the free energy have very different size, and something that you pointed out at the first seminar I heard when I was here. That is, these terms in green are, once you non-dimensionalize everything, are of the order of 10 to the minus 7, 10 to the minus 6, while the terms in black are order 1. So, and this, as I said, is independent of the details of the free energy. You can have 3 elastic constants, 33 elastic constants. The end of the story is that these terms are small, provided that the gradient is small. And so this difference in size is both a problem and an opportunity. Okay? And that is what we want to exploit. Okay? It is a problem because it ultimately makes the equation for the liquid crystal stiff. It's an opportunity because we can use this huge separation of scales in order to do something analytic with it. However, and here is the main limitation of what I'm going to talk about, this term is small if the gradient is order 1. So if instead the gradient is order 1 over psi 0, then this term is order 1, and so all this separation of sizes falls on its face. Okay, so I'll come back to that. And so how do you obtain the equations for motion? Well, you obtain the equations for motion by minimizing this free energy and introducing some sort of dissipation. Yeah?
What's the meaning of the notation?
Yep.
Trace
This is the trace of the product of, so TP, TQ, and TR are these basis tensors. And so these are, well, if you have, so the tensors are orthonormal with respect to the inner product, which is trace of TP, TQ. And so in that case, this allows you to simplify this term here. And well, you have now an overview of everything I'm going to say for the next. That's not your fault, it's mine. So this is essentially is what comes. Yeah, what comes from the cubic term of the free energy. And you can derive an equation of motion, and the green terms will give you this green term here, and the black terms will give you this term here. And this is very small, and to emphasize that it's small, I multiply it by eta, where eta is my smallness parameter. Okay. I tend to use eta instead of epsilon because I normally use liquid crystals with electromagnetic fields, and in electromagnetism, epsilon is sort of sacred.
Can you say a bit about the cubic term in 2D?
The cubic term in 2D is not there.
No, so this free energy that you were talking about,
This is for the 3D case. In 2D, it simplifies considerably.
yeah.
And
And you're going to deal with 2D?
I'm going to show you the equations. I'll do essentially explain how the method works in 2D, and then say that it can be extended in 3D. But this is, if you want, this is in the free energy in its full glory. So, as I said, the green terms are very small. That's why I multiply them by eta. And so these equations are numerically stiff because you have to, essentially this term is order 10 to the minus 6 or 10 to the minus 7. And so you have to have a time scale for tau, which is 10 to the minus 6, 10 to the minus 7, even though you want to integrate the time scale of length 1. Okay? And so what we have done is to try to essentially use a perturbation technique that separates these two scales. And this works, but as also said before, this works provided we are away from defects. So it's an approximation technique that is valid away from defects. So what I want to do now is just give a simple-minded introduction to the slow manifold. I realize that this may be a little bit too trivial for this audience. But on the other hand, it is what is at the core of this approximation. And so I just wanted to illustrate what I'm doing and what we're doing and so on, even though it may be a little bit too simple-minded. So let's consider this system of equations here. So x dot is, if you want, the slow variable. X dot is a derivative is eta times a quantity order 1. So this x dot is a quantity order eta. Y dot instead is just a minus y plus x squared. I've chosen these just because the algebra is simple. So how come this problem is stiff? Y evolves in a time scale of 1. X evolves in a time scale of 1 over eta. But it's also very easy to approximate because what we can say is that if we are interested only in the slow time scales, Y equilibrates. So if you're a physicist, you say that you can do an adiabatic elimination. Y relaxes to an instantaneous equilibrium. If you are sort of a background in dynamical systems, you can say that you can apply a kind of center manifold theory if you are, instead of background of perturbation theory, you can apply a method of multiple scales. The end of the story, that these are really three names for the same thing. What we end up doing is saying, okay, y relaxes to the instantaneous equilibrium, so I'll say that y is equal to x squared, so that the bottom equation is satisfied. I replace y equal x squared in the top equation, and this is the equation of slow time. Okay? You can add bells and whistles to it, but this is at the heart of the problem. And does it work? Well, yes, it does work. First of all, it's no longer stiff. There is just one time scale. And if you want to compare it, this is the case eta equal 10 to the minus 2. This is equal to 10 to the minus 3. So if you take this case, what we were saying is that y relaxes more or less instantaneously to its equilibrium value, and then x moves slowly along this red curve. Okay? And this t95 is the time it takes any of these initial conditions to reach 90, to be within 5% of the red curve is 5 units of time of the fast time, and we are integrating for 1 unit of time only of the slow time. So in this case, using the slow dynamics gives you really a factor of 200. Now that is how the method works algebraically, but it's more instructive to see how it works geometrically, okay? Because then we can use the geometry to understand what to do with the liquid crystals. So this is again is another toy example. If you look at it, you can see that it is essentially a motion along a circle. It's a motion on a circle with that is very slow. This fixes you on the circle, and this gives you very slow dynamics along the circle. How can we see this? Well, we see this by going to polar coordinates. If we rewrite this equation in polar coordinates, you get an equation for the radius that is independent of anything. It's just r dot equal r times 1 minus r squared, and an equation for theta, the angle of the polar coordinates, instead is slow. And so what you can see from this equation, if you look at it, is that the r variable, the radial variable, will converge to 1 pretty quickly, and what that is a circle of radius 1 pretty quickly, and then you will move on this circle slowly driven by this slow equation for theta. Okay? So we can apply the same story as before. That is, we can solve the equation for r. The solution is r equal 1, and substitute it into the equation for theta, and then we get that there are two equilibria, one at 0 and one at pi, and the stable equilibrium is the theta equal pi. So we can essentially, this, if you want, is the slow invariant. Oh, I'll get that. This is the slow invariant manifold, and if you start with one of the initial conditions, you move very quickly over towards this circle, and then you move very slowly towards this point here. And so the equations for the slow motion are these equations here, and then you can notice that there is a y that you can collect from both terms, and so you can write these equations in this form. And the vector minus yx is the vector tangent to the circle. So what this is saying is that the slow motion is in the direction tangent to this invariant manifold, okay, and modulated by some factor. So it's vector tangent to the manifold times a scalar factor, okay. And so we can interpret this as the force that drives the system along the manifold. So this is an example, and on this I'm indebted very much to David, of what is called a Signorini expansion. This is a photo that I got from Wikipedia of Antonio Signorini, who was a mathematician that also got a degree in civil engineering, in the essentially active in the period between the two wars and after the war. Notice the bow tie. And so he developed this expansion and in the context of elasticity, and then it was expanded or extended by various people, including David, to a more generic framework. The case that he was interested in is an elasticity case, but it's the problem of having a system that in an unperturbed form has a continuous symmetry. But then there is a perturbation that breaks the symmetry. And so if the system has a continuous symmetry, like in this case, then it has an orbit of fixed points. Okay, so if you take the example of the circle that I've used before, this is the unperturbed system. It has essentially a circle of fixed points at r equal to 1, which correspond to the O2 symmetry of this problem. Then you switch on the perturbation, and the effect of this perturbation, which is this term in eta, is to break the O2 symmetry and reduce this invariant circle of fixed points to just 2, of which one is stable and the other is unstable. And so, as I said, Signorini developed this in the context of elasticity, but this can be extended to a much more general framework. And so what we are doing is essentially using this method. I should point, just for completeness, that this is true provided that some technical conditions are satisfied, but if you're really, really interested in the technical details, you should ask the person there in the middle. They're too difficult for me. And so in the case of liquid crystal, this is the equation we have to study. Well, f of A
Sorry, tau here, what was the tau, meaning of tau?
is in this
A over what?
of a tau. In this case, it's a type, it should be t. It should be time, but I use t for the fast variable and tau for the slow variable, but as it's written, this should be a t.
But how it could be that this tensor moves in free space, no hydrodynamic, nothing around?
I don't include any hydrodynamics, no. But essentially, I consider just the relaxation of the liquid crystal towards its equilibrium, without including any hydrodynamics. What we want to include the hydrodynamics at a later stage, but not now.
But Giampaolo, are you actually thinking about this as a sort of, at the moment, this is an artificial time?
This is an artificial, is the usual,
designed to find equilibrium.
Yes, it's the usual approach of saying I have a free energy, I need to find a free energy, a minimum of this free energy. Well, I'll introduce a rotational viscosity and assume that the system relaxes toward the equilibrium, which is the minimum of the free energy. So that time there is this, if you want, it's artificial time. And in this particular case, as I said, this should, since I've written this equation, this should be a t because it's a fast time rather than tau, which is a slow time. Okay? But so going back to this equation, the unperturbed problem is just this f of A, which has either an O2 or an SO3 symmetry, depending on whether you're in 2 and 3 dimensions. And then the effect of the elasticity, the applied electric field, the boundary conditions, is this perturbation that breaks the symmetry. Okay, so from a more general point of view, the perturbation scheme that I'm discussing is an example of the Signorini expansion. So how does the method work? In summary of the examples I've given you, well, we essentially expand the variables x and y in a power series of eta. Then we determine the slow manifold. We determine, if you want, the instantaneous equilibrium manifold. And then we determine the equation for motion on the slow time scale on this slow manifold. The added bonus that I have not discussed in these examples is that if you then compute the corrections, you have an idea of how good your approximation is. Okay? And so if you want, is a system that allows you to do some self-checking. Okay. So you can not just eliminate the fast time scale, but from a numerical point of view, it also gives you a warning bell to when your system, your approximation may fail. So how does it work? I'll do it, as I said, I'll do it in 2D. The reason I want to do it in 2D is because in 2D we can easily draw. It's a planar system, and so we can just sketch everything. And so in 2D, the equations for A become extremely simple. This is the, if you want, the fast part. A man is what comes from the Giampaolo-Landau free energy. And this is the slow part, the elasticity and the coupling with the electric field. Okay, is that the answer to your question? And so we now apply the same principle that I've discussed before. That is, we expand A as a power series, so we'll say that is A0 plus eta 1 plus terms order eta squared. Then we just consider that terms order 0, and I assume that they have reached equilibrium, so I just have to solve this equation, the equation in black, which is, equal to 0. Well, the solution of this is that the components of A must be on a circle. A must be on a circle of radius 1, okay? and which, since the scalar order parameter is the sum of these two squares, it really means that in this situation the scalar order parameter is fixed, is a constant. Okay? So this is the circle of radius 1, and this defines the eta equals 0 invariant manifold, the order 0 invariant manifold. So the solution, and this dotted line, dashed line, blue line, is a real numerical simulation, converges rapidly towards this circle and then moves slowly along the circle. Okay, so the approximate solution that we will obtain in the next slide is fixed on this circle. The exact solution is just a little bit further away from the circle. And the motion along the circle is on a time scale, on a slow time scale. And so then we want the slow time dynamics, so we do this by going to next order. And if we do this, so we now include we take this equation and expand it to next order. We linearly take the linear terms in eta, and what we obtain is that the correction, the equation, we obtain a correct equation for the correction to the perturbation, that is for A1. So it says that some linear operator applied to the A1 is equal to this, and then occurs is the usual story in the method of multiple scales and so on. We want this equation to have a solution. Therefore, the right-hand side must obey a solvability condition, and this gives us this slow time dynamics. I don't really want to do the algebra, I just want to give you the geometrical picture. And so the geometrical picture, you can obtain it by decomposing this term here in a term that is tangent to the slow manifold and a term that is normal to the slow manifold. The one that is tangent will give you the slow time dynamics towards the equilibrium. The one that is normal will give you the magnitude of the correction to the solution. So let's say that this is L for one particular value, this driving force for one particular value of the order 0. And so if we are if you suppose that the initial gas has collapsed rapidly to the slow manifold, then it moves slowly. Why does it move slowly? Well, because if you're in a position like this one, then L has a large component tangent to the manifold, and it makes it move along the manifold. And then it drives it along the manifold to reach a point like this one, where L at this point is completely normal to the manifold. So there is no further motion along the slow manifold. You have just a component along the normal to the manifold that gives you the correction to the your approximation. Okay. And so this is from a geometrical point of view. If you do the algebra, if you do the calculations, then you obtain an equation for the slow motion of the slow manifold. It says that the evolution of A0 over the time scale order eta is this this scalar factor, okay, which involves the Laplacian of the components and the coupling with the electric field in the direction tangent to the manifold, which is the same form as the example of the circle that I gave you before.
It's square of electric field in your case. It's E square, real physical.
Yes, is a trace E1 and E2. Sorry, I haven't said this. What we do is we write E as a traceless symmetric tensor. Okay? And then E1 and E2 are the components of the basis of the traceless symmetric tensor of the tensor E. Okay.
And did you assume some specific boundary conditions?
The boundary conditions we will impose on this. Okay, so but these are the equation, and then you have to say what is the domain, and so A0 will obey some boundary conditions, and that is what drives the slow dynamics. Okay, so the dynamics is driven by the elasticity induced by the boundaries and by the applied electric field. Okay. And so we call this a defect-free Q-tensor approximation, where defect-free is because all this is predicated on the assumption that the elasticity term is much smaller than the thermotropic term, and so this is no longer true near defects. Okay? And as I said, the n component, the component normal to the manifold, gives you the correction to the approximation. And in 2 dimensions, it's quite nice because you can compute it analytically. That is, the correction to the scalar order parameter is given by this expression. So you can analytically determine how big is the correction to your order 0 approximation, and if it's from a numerical point of view, if it is too big, then you know you're in trouble and you should really do something else. Okay. Is this accurate? Well, so all this started really from a problem that Małgosia had posed us. Małgosia is an experimentalist, and she was interested in beam coupling in photorefractive liquid crystal cells. So these are cases where there is a periodically modulated electric field in this direction, and so these are the equipotential lines. The black lines are the equipotential lines. And so we thought, okay, we'll use this as a test case. So this is a result of the, I think it's a result of the approximation, but I'm not sure. It doesn't really matter. I'll show you why in a second. But so the idea is these are equipotential. They are spatially modulated, periodically modulated along this side. This is into the cell, and the potential on the other side of the cell instead is constant. Okay? And the little blue lines represent the orientation of the liquid crystal. And so, as I said, this was obtained, I guess, using the upper equation before. But what I'll show you next is the error. So this is the magnitude of S1, the correction, estimated using this equation here. This is the difference between the approximated solution and the numerical solution. Well, first of all, the S1 is a fairly good estimate of the error in the sense that when this is higher, this is higher. But then you should also look at the color bar. This -4, -5, -6, -7 are the logarithm base 10 of the error. Okay? So the largest error is smaller than 10 to the -3. Okay? So that is how it works in 3D. In 2D, in 3D is exactly the same thing, except much more complicated. Why is it more complicated? Well, first of all, because the equations are more complicated, and secondly, because there are more things to take into account. For example, there is not just a scalar order parameter, but the biaxiality order parameter. And so the equilibrium leading order solution, okay, is a manifold with constant scalar order parameter and constant biaxiality. Then in most liquid crystal systems, the free energy is such that at order 0, the biaxiality is 0. And so this says that the manifold, instead of having 3 dimensions, has 2 dimensions, is what I call this cannellone to spaghetto transition, in the sense that the cannellone is a cylinder, okay, and so you can define an angle on the surface of the cylinder. Spaghetto is a one-dimensional cylinder, is a wire, and so the angle is no longer relevant. Okay, so we have to take into account of all this and then define a convenient parameterization for the space tangent to this manifold. But it can be done, and it works. Again, this is again a cell like the one I showed you before, with modulated modulated potential on one side and constant potential on the other. What we've changed is the boundary condition. We assume that the liquid crystal is perpendicular on both sides. It plays a planar alignment, but perpendicular to the plane of modulation of the electric field. And what in the periodic boundary conditions on the other side. And what the electric field does is essentially tilt the liquid crystal forward. Okay? And so this is what this plot shows. This is a view from the top. The boundary conditions, as I said, are perpendicular here, and so you can just see dots here and dot there. And then the electric field just bends the liquid crystal in the plane, and so you see these straight lines. And here you see it from an angle. And again, we've done, this is a simulation using this approximation, and this is the comparison of the estimate of the correction. In this case, you cannot obtain the correction analytically, you have to do it numerically. And this is the difference between the approximation and the numerical simulation. Again, 2 things. The correction is a good estimate of the error, and both of them are pretty small, at least for this case. This is again a scale -5 to -8 on log base 10. Okay. So that's the work we have done, most of the work that we have done so far. The main drawback of this is that it does not allow you to include defects. Okay? In a sense, is somewhat a glorified version of using just an n version of just a director field n, in which you parameterize the director field by an angle or 2 angles if you are in 3D. From my point of view, it has the advantage that it is still a Q-tensor theory. You don't have to bother with all issues with n equal to being equal to minus n. But at the end of the story, if you really want to be nasty, then you could say, well, this is really just a glorified director field. So what we really want to do is to include defects. And what we have done, just to see if it works, is to include a stationary defect. So this defect-free Q-tensor approximation models the liquid crystal away from the defect. So suppose that I have a defect, like in this case. Well, what I could do is essentially divide my space into two parts. The part near the defect, I'll just cut out. And the part away from the defect, I'll just use the approximation, and that I can do. And then in the region around the defect, I will have to use the full Q-tensor theory. This is still advantageous from a numerical point of view, because I have to use the Q-tensor theory only in the very small region where the defect is, and all outside I can use something else. And we can do this, and we can do this either analytically, if you want, by saying, okay, I've managed somehow to solve what is the equation for the defect in this region, or otherwise numerically. What we have done it numerically. So what we've done is essentially created a bulk grid, a defect grid, and then a composite grid, which is a combination of the two. We have solved so if you want, these are the grid points on the defect grid, while instead on the bulk grid, they are the coordinates. And so in the bulk grid, we do not consider the points near the defect. In the composite, in the defect grid, we do not consider the points outside this region. And then in the composite grid, we do a weighted average of the two. And so that is what we've done here. This is a solution on the inner region using the full Q-tensor. The scalar order parameter is plotted on the vertical axis, goes from 1 to 0. This is the solution of the approximation in the outer region. Notice the vertical scale. In this case, the scalar order parameter is essentially flat, but the vertical axis goes from 1.05 to 0.95. And then this is the weighted average of the two, which describes the region with defect. Okay?
When you solve the outer case,
Yeah.
you have a boundary condition on the join, which is dependent on the solution in the inner part.
Yes. So essentially, what you use is that the boundary condition. I'm trying to remember because we did this quite a long while ago. But if my recollection is correct, in the overlap region, essentially we use an average of the two as the boundary condition for the two equations. Okay.
You have to do that iterate.
Yes, but this in any case is evolving in time.
Yeah.
And we are still just interested in reaching an equilibrium. So provided we reach the right equilibrium, we don't particularly care what happens in between. So this works, but it is a bit of a cheat because, well, we've put the defect there. We've chosen the boundary condition so that the defect had to be there and could not move. Okay? So the real trick, and what we want to do now, is to track the defects. We should be able to track whether they're born, whether they die, whether they move. And in this respect, we plan to use a correction to the scalar order parameter to give us some indication whether this is possible, whether a defect can be forming or not. And the other possibility that we are exploring is the idea of regularization. This is an idea that we borrowed from some colleagues of ours that do general relativity. In modeling of black holes, well, there are huge singularities, which is the black hole, but there are some analytic solutions for isolated black holes in the universe. And so if you now want to study a black hole with something else around it, which is not too significant with respect to the black hole, well, it's still a singular problem, but what you can do is you can subtract the isolated black hole singularity, and you're left with a problem that is more regular. And so the idea here would be to see whether we can do the same for the defects in liquid crystals. And the other thing is to come back to your question of time, that is, yes, can we include the fluid dynamics in the model? In principle, this is something that we have started doing partly with Keith, partly with Giovanni De Matteis, is to consider, okay, imagine that I have a liquid crystal without defects, but it's moving. Can we then does this invariant manifold still exist? And then so can we do this approximation? And then, of course, if we ever manage to include the defects, then we will have to include the fluid motion in that as well. And then if I live long enough, then we could also consider the effect of having nanoparticles in this. So the conclusions is that we have a fast and accurate algorithm for liquid crystal alignment away from defects. I should say that it is fast. It is a simulation. The approximated simulation takes 100 times less time than the full numerical simulation for those plots. It is accurate, provided, again, as I said, there are no defects in sight. We are working to extend this to include defect fluid dynamics and so on. It has taken a rather long time to do that, but we have now someone that is actually going to do the work. Yogesh, some of you may have met, arrived last month, and he has a 3-year contract to work on this. It took 2 years to get A, the money, and B, the body, but we are there now. And if you want more information, especially about the 3D case, A, you can talk to me. Otherwise, this was published in Science. And if you want to play with the code, it's available at this website. That's it.
Thank you very much, Giampaolo. Is there any?
If you are doing anyway numerics, why not to consider not one constant approximation, just to move to more realistic?
We could. It's just,
of course, yeah.
It's they essentially including more than one constant is dead easy, because the only thing that we have to do is it's dead easy.
But defect structure will be completely different.
Oh, sure. So, but what I meant to say is that the only thing that changes, if you have one elastic constant, okay, it makes in 2 dimensions, you just have this very nice and little approximation. If you have 2 or 3, this will be more complicated, but the structure will be exactly the same. The only thing you change is the driving force, but not the structure of the manifold. Including the defects instead will change the structure of the manifold. Yeah.
Margherita?
How does it compare? How does your algorithm compare with some kind of adaptive mesh scheme? So if you solve the full problem with meshes which are much smaller.
Yeah. I haven't done a direct comparison because I don't have such a scheme to compare it with. These are simulations in rectangular domains, and so we tend to use spectral methods. So I can't really answer that question. My guess, though, talking to Hannibal and so on, they cannot integrate very big domains. And even though they have a very refined adaptive mesh scheme. Now, their code, of course, includes also fluid dynamics and all the bells and whistles you can imagine. Here, if you are, in a sense, if there are, in the regions where there are no defects, this equation is, as you gain essentially automatically a factor of 10 to the 4, 10 to the 5 because of the time scale. So I don't really know whether an adaptive mesh scheme could be able to compensate for such a huge difference. The problem is really the scale of the time step. But I can't give you a quantitative answer.
Ibrahim?
Have you tried to compare with the results for 2D Ginsburg Landau, right? Because we all know what happens, and it's completely equivalent. So we know the logarithmic interaction of vortices, or how the vortex would interact with the boundary. Can you reproduce logarithmically slow?
This cannot include any vortex at all.
Well, you mentioned that there is this sort of composite scheme. So
yeah, but for the moment, the only composite scheme I've done is one stage that the boundary is in a circle. The boundary conditions have been chosen so that there is a defect dead in the center of the circle and it doesn't move.
Oh, okay.
So you are saying that you did this case with a defect, but there you had to use some adaptive mesh, right?
No, not adaptive mesh, composite.
Okay.
In the sense that in one region I solve one equation, and in another region I solve another equation.
Okay.
And then the solution is a composite of the two, a weighted average of the two.
Right. So when you choose the boundary between the two regions, what's the size in terms of psi naught?
My recollection, sorry, this simulation was done quite a while ago, is that these are the grids.
Yeah.
So you can, these are the points, if you want, these green points are the ones that are excluded from the outer region, the orange points are in the common between the two.
Right. Now, I'm saying this because I think the optimal the optimal radius for that green disk would be something of the order of psi naught at
Yeah.
a power less than 1. Right. I mean, because I can tell you more, but I think that would be optimal.
Yeah, well, sorry, I'm happy to discuss it also because
Yeah.
in your talk you mentioned this.
Yeah,
You had
basically we
something
did-
like this, and you mentioned this R terms and so on that I didn't really understand.
We did the same thing in the stationary case, and there, essentially what we see is that if you stay at the distance of the order psi naught from the defects, psi naught in your notations, beta or square root of psi naught, say, then you can use this kind of approximation that you had. Right, so we did this thing in the stationary case, but I expect it holds in the dynamical case as well.
Okay.
So, yeah.
Nigel?
Have you thought about just solving for the defect once only, and then treating it as an object, and then moving it around? Because you could work out
That
the
is
force on the outside of the defect from the outside structure.
That is the idea behind the regularization scheme.
Oh, right, okay.
You solve, in the case of the general relativity in black holes, they have the analytic solution for the isolated black hole. In this case, well, Yogesh is working on this now, there are analytic solutions for isolated defects and so on, but at the end of the story, we could also solve the defect numerically, and then subtract this numerical defect from the field, and then integrate numerically the equation for the difference.
When you say subtract, you mean that you need it to match appropriately the boundary conditions. I mean,
I'm guessing. My hope is that we don't have to do it exactly, because we don't want to. Like in the black hole case, it's not that they get the solution; they get a field that is more regular than the one without subtraction, and that then they can solve more easily. In a sense, what I would hope in this case, but for the moment it's just a hope, is that okay, if we don't have a perfect matching, then there will be differences between if you want to, but there will between the real field and the field we're integrating, but their differences will be more regular than the defect, and so will be compatible with this idea of having a slow manifold.
the only thing I'm worried about would be that in such a way you might introduce kind of residual stresses in the boundary region between the defect treated as an object and the surrounding,
Okay.
which do not necessarily disappear during the evolution. I mean,
It could be. Sorry, as I said, we haven't done it, and so
I think there is a similarity with the quasi-continuum method in studying fraction and dislocations, say in a solid. And in that case, they have focused on exactly dealing with these residual stresses, where you match your computations around the defect and outside. So I don't have an intuition of whether in this case it would be much harder than, let's say, in a situation with a crystalline structure. But that, I think, it would be a good point to
talk about it.
Yeah.
Tim,
If you're just interested in the strategy for minimization is to go downhill, in some sense, right? But if one was trying to minimize, if one was only trying to minimize, one might well want to use some kind of Newton method, rather than right. I mean,
Yes.
right. And on the other hand, if one was regarding this as the first stage in doing fluid mechanics, then one would want to stick with this method on the grounds that, as it were, the minimization is a sort of trivial job because we really want to.
There are two issues. One is, yes, this would really be the first step to include also the fluid motion, and so the time dynamics, so that the time dynamic becomes real time. And the other is that, at least from a personal point of view, I prefer this kind of method to find the minimum of the free energy to a parameter space exploration of an optimization scheme, just to avoid minima. Sorry, not avoid minima, I don't want to avoid them all. but local.
Local mean.
Local.
But nevertheless, the point is that a Newton scheme as opposed to an iterative. I mean, this is like an iterative scheme, right? Whereas a Newton scheme would be
No, so
expected
this
to
is
be
more
much
a
faster.
relaxation scheme. Where
Yes,
Newton would be more
yeah,
an
it's a
iterative
relaxation,
scheme.
but right, but a Newton scheme would you'd expect it to be much faster.
Not necessarily. My limited experience with using a Newton scheme on a problem similar to this was that it took forever to converge, and I wasn't never entirely sure what it converged to. But I haven't used them much.
But of course, the initial guess is
Yeah.
Probably the separation of timescales would work probably in the same way, but it would be a different set of equations to the ones that you've written down. That's it.
I think what you would have to do then is you would have to set your Newton scheme. Essentially, you choose your guess of the manifold, your initial guess on the manifold, and you choose your Newton scheme so that all the guesses that the Newton scheme makes stay on that manifold. And then I think you would be okay. Otherwise, if you don't take into account of this, then the elastic term is a very small perturbation that I think may be lost in the numerical noise. But then, as I said, I'm guessing a bit.
Other question? And I have one. I mean, going back to the Signorini's scheme, if my recollection is correct, Signorini's scheme is for statics.
Yep, I think so.
And it is based on this expansion, formal expansion, and on the famous or infamous compatibility, Signorini's condition, which is a compatibility for the loads, for the scheme to be applicable. Now, my question is, which is, in your case, the equivalent of the compatibility Signorini's condition, and second is whether in the dynamical evolution, the compatibility condition, which might be satisfied at initial time, is not assigned a further time, and so the justification of the formal extension breaks down on the way.
I never thought of that. Let me think for it. The key
Yes,
assumption
this reminds me precisely
Yeah.
of Signorini's compatibility condition.
and the only assumption in this scheme pass. Sorry, I haven't thought about it in this term. The only assumption that is obvious in this scheme is that there are two of them, that there is the separation of scales, that this is a small perturbation, and the other is that this equation is well defined. Now, if I had to guess, is that the Signorini compatibility condition is, I think, how this equation is defined. But
Kind of, I think, my recollection is that something should have been in the appropriate range, which is precisely what you said, kind of Fredol condition.
yeah,
And
the fact is that there wasn't really, when we solve for this, there is really never any problem. We impose a solvability condition on this equation. There wasn't really anything we had to be particularly careful of. Now, it could be because we didn't see it. And so, but it is.
my only concern is maybe in the presence of a defect, this compatibility condition might break down during the evolution.
Okay.
So the scheme might be in kind of danger. But
Okay.
these are very vague recollections of this very famous paper by Signorini.
Do you actually have the paper?
Oh yes. I
Oh.
still remember
Because I've
remember the title. Actually, it is a series of papers, and the title it is an Italian paper written in Italian, and it is a long paper. It is a series of 3 papers, and the title of the series of papers is I was forced to study them. Just what in Italian sounds trasformazioni termomeccaniche finite. That's the title. And the idea is that it included also thermal stresses.
Okay.
And it was a general scheme of approximating nonlinear elasticity with a sequence of linearized problems, and in fact, there is a hierarchy of linearized linear problems which actually arise at various powers of the
I
time.
would like to have a copy of the paper because I noticed that a lot of people cite the paper of 1931 and so on, but it's one of those citations that is untraceable. It is procedimento di archivi, archiviazione meccanica razionale, and so on. And I thought, well, this is a paper I could actually read. It's in Italian.
This is perfectly appropriate semantic for your case because it's not dynamics. It's indeed it's thermodynamic or thermomechanics what you are doing. It's not dynamics at all. It's thermodynamics. It's equilibrium state you are looking for.
Yes.
And precisely what the title of that paper.
His library is amazing.
Well, thank you.